This is a chem study film, a production of the Chemical Education Material Study. When most people look at substances, they normally notice only the bulk properties, such as shininess, shape, or hardness. However, when a chemist looks at substances, he often visualizes them in terms of atomic and molecular models, which interpret the bulk properties in terms of atoms and molecules and the way these pack together. For example, this is crystalline mercury and its model. Here is ice and its model. And here is a model of liquid water. This is a model of solid carbon dioxide, or dry ice. Such models indicate a shape and orientation for the atoms or molecules, but no motion is shown. Yet, we know that solids melt to liquids, as does this crystalline mercury. And we know most liquids are quite fluid. Other crystals, like carbon dioxide, change readily from solids directly to gases. The cold, gaseous carbon dioxide condenses water from the air to give a white fog. Properties such as volatility and fluidity suggest that molecules have motion. If so, static, space-filling models do not fully represent the properties of substances. Let's return to the mercury sample and look for evidence of molecular motion in it. Heating converts the apparently stationary solid into a fluid liquid. Upon further heating, the mercury boils. A condensate of liquid mercury appears. Apparently, gaseous molecules were formed, moved away from the liquid surface, and condensed to liquid at the top of the tube. The rigid model shows structure, but it is inadequate to account for properties involving motion. But here is a model in which motion is apparent. It consists of about 3,000 small glass beads sandwiched between two pieces of glass. To simulate the effect of temperature, we shake the model with this agitator. The beads jostle about, bumping into one another and occasionally moving past one another. There is no apparent order to the structure. What you are seeing proves to be a rather good model of atomic motion in a substance like liquid mercury. We may simulate cooling by decreasing the mechanical agitation. A remarkable change occurs. The beads assume highly ordered positions. The model now illustrates the regularly packed structure of crystalline mercury. Close inspection reveals that the glass beads are still oscillating, just as do the atoms in real crystals. The motion decreases with decreasing temperature, but slight oscillation continues even at absolute zero. Let's increase the agitation, simulating a rise in temperature. Motion increases. Large blocks of atoms move with respect to one another, but atoms in a solid seldom exchange places or intermix. Further rise in temperature increases the motion, until finally, at a sharply defined level of energy, or temperature, the solid structure disintegrates, just as did the solid mercury. The melted model has become fluid, due to the larger amount of open space and the smaller degree of structure present. We have the random orientation and disordered motion characteristic of liquids. Now let's consider the molecular motions in the transition from liquid to gas. The mercury tube has been modified slightly by introducing bits of blue glass which float on the mercury. As the temperature rises, the increased motions of the mercury atoms jiggle the pieces of glass. But look what's happening now. The pieces of glass rise and undergo vigorous agitation. Why? Mercury atoms are leaving the liquid and condensing at the top of the tube. Such motion from place to place is called translation. The moving mercury atoms bombard the glass particles, causing the bombarded glass to bounce about. Let's look at translational motion at the molecular level. Here, in very slow motion, we see models of several kinds of gaseous molecules undergoing translation, that is, motion from place to place. In addition, most of the polyatomic molecules have a further kind of motion, rotation. And close examination shows still another kind of motion, vibration. Rotation and translation involve only molecular tumbling and simple motions through space. But vibrational motions can appear complicated, as in formamide. Here is water undergoing one possible vibrational pattern. But every actual vibration can be considered as a combination of simpler vibrations, in which the atomic motions repeat over and over again. In one motion, the bonds stretch in an unsymmetrical fashion. Here we have a symmetrical stretching vibration. A third vibration is mostly bond bending. All are simple. The frequency of each vibration is determined by the strength of the bonds and the masses of the nuclei. When the nuclear masses increase, as in heavy water, the vibrations slow down. The simple vibrational patterns combine to give the more complicated actual vibrations. The total molecular motion can consist of various combinations of vibrations, rotations, and translations, which can be changed by a collision. Note the increased amplitude of vibration, indicating greater energy in the molecule. Or the amplitude of vibration could decrease when the molecule loses energy. The energy content can also increase by absorption of light, or decrease by emission of light. Not only the total energy of a molecule, but also the distribution of its energy may be affected by a collision. Simple motions may result, or more complicated ones. Here is a mechanical system in which polyatomic models are being jostled about. The lack of order and the close contact make this approximate a liquid model, rather than gas or solid. In a liquid system, the molecules are much closer together than in a gas. Hence, the molecules collide more often. But the resultant motion for complicated molecules is again a combination of molecular translation, rotation, and vibration. The effect of the jostling on molecular motions can be seen more clearly if we introduce a marked model. The marked molecule can move from one place to another only very slowly, because there is so little open space between the molecules. Thus, the net translational motion in unstirred liquids may be very slow, even though vigorous molecular motions are occurring. Consider this experiment. To aqueous ferrous ions, we will add aqueous purple permanganate ions. Pouring causes efficient stirring, and a rapid reaction occurs, as shown by the color change. But what happens if we use a crystal of potassium permanganate? The crystal drops to the bottom of the ferrous ion solution almost unchanged. Once on the bottom, the permanganate begins to dissolve, but only slowly moves away from the solid. Even 5 minutes later, little motion into the solution has occurred. Molecular motion in a liquid is restricted by the close packing of the molecules. Stirring, of course, aids the molecular motion in mixing the ingredients. Rapid reaction then occurs. Let's do a similar experiment, dropping a vial of bromine into a cylinder full of air. Diffusion is more rapid than in the unstirred liquid. The large open spaces between the gaseous molecules allow each molecule to move rather freely and to intermix quite readily. Net translational motion through gases, as contrasted with liquids, is more rapid. In solids, molecular intermixing is very slow indeed. Here is a rock whose layers have been in close contact for many millions of years. Any intermixing must be extremely slow. Thus, if we mix solids, for example sulfur and zinc, we expect very slow, if any, reaction because of the restricted molecular motion and the very slow intermingling of the molecules. But if we place the mixture in a porcelain dish and heat, molecular motion increases. But intermixing still does not occur until the sulfur melts. Vigorous reaction follows as a result of the increased molecular motion. Now consider reaction between two gases. The red balloon contains oxygen, the blue one, hydrogen. The gases mix easily. In the resulting solution, the intermixed molecules are colliding freely, yet reaction does not occur. But if we supply additional energy in the form of a flame, we have a very fast reaction indeed. Thus, our usual static models illustrate a great deal about structure, but dynamic models indicate that molecular motion is always present and increases with rise in temperature. The freedom of motion also increases from solid to liquid. Polyatomic dynamic models allow us to interpret liquid behavior in terms of the slow intermixing of molecules, even though they may be vigorously translating and rotating. Even more freedom of motion is possible when the molecules are widely separated, as in a gas, where translation, rotation, and vibration occur almost unhindered. As intermixing and molecular motions increase, the ability of molecules to react also increases.